All right, homework number one, problem number one. We're turning this into set builder notation, and there's more than one way to do it. But the way I generally like to do it is you're creating a set, and then you have some essentially a function that transforms x into whatever we have here, whatever will map from the natural numbers to one of these numbers in this set. So we can tell that, there's some kind of squaring going on because this is the square of 3, square of 5, square of 7. So it's not exactly x squared, but it'll actually be 2x minus 1 squared. So that is the formula essentially to map the natural numbers to the set right here. And then we just draw a line. This is essentially saying the set of, this formula here such that x is an element of the natural numbers. And then that's it. We just need to close that off. So we're basically saying that x is going to be equal to 1, 2, 3, etc., all the way up to infinity. But we just basically plug that x into here, and we get whatever it is. So we start out with 1, and then 2 times 1 is going to be 1 squared, and that'll be 1, which is the first element in our set. Do note that 0 is not considered a natural number. And obviously none of the negative numbers are natural numbers. So that's all we need to write for this right here. Number 2, same thing. We just need to figure out what the mapping is from, 1, 2, 3, etc. to what we have here. Obviously we have 1 over 2, 1 over 4. So it looks like it's going to be 1 over 2. And then we're going to take the x here. That is going to be the formula to map. Here we want to say this is the set of all 1/2 to the x power such that x is a member of, this one we want to do the integers, but we also want to have the constraint that x is greater than or equal to 0. And the reason for that is because we do want 0 to be included in our set as an input value. So when we plug this in, it'll be 1/2 to the 0, and then that will just be equal to 1, because anything to the 0th power is equal to 1. And then you have, 1/2 to the first power, 1/2 to the second power, which is just going to be 1 over 4. And then you have 1/2 to the third power, that's going to be 1 over 8, etc. And that will build out this whole set right here. But essentially all we have is our formula that maps, x to this set right here, and then on the right side we just have all the conditions that we need for x. Now for this one we're doing the Fibonacci numbers. There's more than one way to do it. If we want to do it the way we've been doing it, we can do, so this is f sub x minus 1 plus f sub x minus 2, and then we have x, and then is an element of the natural numbers. We have that x is going to be greater than 1. This is going to be a piecewise function. F sub x is going to be equal to x, such that x is an element of the integers, and x is between the values of 0 and 1. We can look at this and make sure it makes sense. If x is anything less than 0, it doesn't qualify for either of these conditions. If x is 0, then we're going to map it to f of x is going to just be equal to x. So f of 0 is going to be equal to 0, and f of 1 is going to be equal to 1. And then for any value of x that is greater than 1, which we have right here, note that we are also specifying that x here has to be a real number. Although we could also just say, x is an integer. As long as we have this condition here saying that x is greater than 1, that would be fine as well. But if x is greater than 1, we have, x is equal to 2. So at that point, f of 2 minus 1 is going to be f of 1 plus f of 2 minus 2 is going to be f of 0, at which point we have that f of 2 is equal to f of 1 plus f of 0, which is going to be equal to 1. And if we continue with that pattern, we'll end up with 1, 2, 3, 5, 8, etc. Alternatively, we can define x naught and x sub 1 explicitly. So it would be this is the set of all x such that x is equal to x sub n, which is going to be x sub n minus 2 plus x sub n minus 1 for n is greater than or equal to 2, where x naught is equal to 0 and x1 is equal to 1.